Right now, a whisper is crossing the dark. It left a spacecraft older than the internet. It is coming from beyond the sun's protective bubble, and it is forcing scientists to rethink what waits between the stars. Voyager 1 was never meant to live this long. It was never meant to get this far. Yet this tiny machine, running on fading power, is still talking, and what it is saying could change how we see our place in space. Stay with me, because the last part of this story is the part almost nobody is watching. Back in 1977, Voyager 1 did not look like the kind of machine that would still matter nearly half a century later. It was built for a very different era. No smartphones, no home internet, no modern laptops on every desk. Just engineers, slide rules, early computers, and a mission that sounded almost modest compared with what the spacecraft would become. Fly past Jupiter, fly past Saturn, send home pictures and measurements, then keep drifting until the power runs out. That alone would have been historic. And Voyager 1 delivered. At Jupiter, it revealed a world of chaos and motion. It found a thin ring around the giant planet and 2 new moons, Thebe and Metis. At Saturn, it found 5 new moons and a new ring. And it gave scientists one of the first close looks at Titan, a moon wrapped in a thick atmosphere. Those flybys alone would have earned the mission a permanent place in history. But Voyager 1 did not stop there. It kept going, faster than its twin, farther than any machine we had ever sent, past the giant planets, past the edge of the familiar map, past the last place where the sun still clearly dominates the environment around it. That is where this story stops being a story about a brave old spacecraft and turns into something much bigger. Because the sun is not just a bright ball in the sky. It is also constantly blowing material outward. This stream is called the solar wind. It is made of charged particles, and it pushes away from the sun in every direction. Over time, that flow carves out a huge bubble in space. Scientists call that bubble the heliosphere. Think of it like a giant magnetic weather bubble inflated by our star. Inside that bubble are the planets, the asteroids, the comets, and Earth itself. At the outer edge of that bubble is a boundary called the heliopause. That is where the pressure from the solar wind is finally balanced by the material that exists between stars. In simple words, it is where the sun's local space environment starts to give way to interstellar space. And on August 25th, 2012, Voyager 1 crossed it. That moment mattered because no human-made object had ever done that before. Voyager 1 became the first machine in history to enter interstellar space, the region outside the heliopause. Not the complete end of the sun's gravity, not the end of every part of the broader solar system story, but the first true crossing beyond the sun's protective bubble. Humanity had put an instrument in the dark between stars. Now imagine the expectation going into that moment. For years, scientists had built models of what that region should be like. Cold, thin, quiet, sparse. Not empty exactly, but calm. A place where very little would happen. A cosmic in-between. The kind of environment you describe with words like still, silent, and smooth. That assumption turned out to be far too simple. And that is where Voyager 1 began to do something no telescope on Earth could do. It was not looking at interstellar space from a safe distance. It was inside it. It was feeling it, sampling it, listening to it. That difference matters more than most people realize. Because there are questions you cannot answer by staring from far away. You have to go there, you have to sit inside the environment and let it touch your instruments. You have to let the universe stop being a picture and start being a place. Voyager 1 did that for us, and what it found next changed the tone of the whole mission. At first, even confirming the crossing was difficult. One key plasma instrument on Voyager 1 had stopped working decades earlier, in 1980. That meant the team could not use the easiest possible test to prove the probe had left the heliosphere. They saw signs. Cosmic rays from outside the heliosphere increased. Particles from the solar environment dropped. But the final proof took time. Then, almost a year later, Voyager 1's plasma wave subsystem detected oscillations in the plasma around the spacecraft. Plasma is just gas so energized that its atoms are broken into charged pieces. Those oscillations told scientists something important. Voyager 1 was moving through a denser plasma environment than the one inside the heliosphere. That was the missing confirmation. The spacecraft really had crossed into interstellar space, but that was only the beginning. What came later was stranger. Years into its interstellar journey, Voyager 1 started helping scientists study the density of the material around it in a new way. Before this, the spacecraft had picked up occasional plasma whistles, brief events often linked to shock waves from powerful eruptions from the sun. Those whistles were useful, but they were rare. Scientists could get snapshots. They could not get a steady running picture. That meant our map of the nearby interstellar medium was patchy. It was like trying to understand the weather in an entire ocean by checking one buoy once a year. Then researchers studying Voyager 1's data found something different. Not a dramatic burst, not a loud event, not some single cosmic scream. A hum, a very faint, very narrow, almost monotone signal. Stella Ocker, one of the researchers who studied it, described it as virtually a single tone. Cornell scientists called it the faint, persistent hum of interstellar gas. It was weak. It was easy to miss, but it kept showing up. And because it kept showing up, it opened a new way to measure what surrounded the spacecraft. That one discovery changed the kind of science Voyager 1 could do. Instead of waiting for those rare solar-driven whistles, scientists suddenly had a more regular signal to track, a running measure, a way to sample the density of interstellar plasma over a very long stretch of space. The 2021 study described steadily sampled measurements across about 10 astronomical units. 1 astronomical unit is the average distance between Earth and the Sun, so 10 of them is enormous, roughly 10 times that Earth-Sun gap. Pause on that. This was not a tiny lab result. This was a direct measurement of interstellar conditions across a gigantic reach of space, gathered by a spacecraft older than most of the people watching this video. And the picture it revealed was not calm. NASA's own explanation used a beautiful image. If the heliosphere is a ship sailing through interstellar waters, Voyager 1 is like a life raft dropped from the deck to test the currents. That image matters because it tells you what scientists were really learning. They were not just measuring one number. They were learning whether the waters outside our solar bubble were smooth or rough. The answer was rougher than expected. James Cordes, another scientist on the study, said the phrase, "quiet interstellar medium can be misleading." There are many places that are not quiet at all. He compared it to weather. Sometimes you get a big burst, like lightning in a storm. But even between those bursts, there is still a softer background, like gentle rain. That gentle rain was the clue. The space between stars was not acting like a dead vacuum. It had texture. It had variation. It had turbulence. It had changing density. And because Voyager 1 was moving through it year after year, scientists could watch those changes unfold in sequence instead of seeing only scattered flashes. Here's where the story takes a sharp turn. When researchers looked at the signal, they found that electron density around Voyager 1 began rising in 2013 and reached much higher levels by about mid-2015. NASA said the increase was roughly 40-fold before settling into a similar range, with fluctuations through the dataset studied into early 2020. That is not the kind of behavior you imagine if you think interstellar space is just a flat, silent emptiness. It means the local interstellar medium has structure, not metaphorical structure, physical structure. Regions with different densities, different conditions, different behavior, a real environment with its own patterns and disturbances. And if that surprises you, think about what it means on a human level. For generations, the space between stars lived in our minds as a blank, a dark pause between the real destinations, a nothing place. But Voyager 1 is telling us that even the nothing place is something. It has a personality. It has motion. It has hidden complexity. If you were the scientist looking at that first steady signal, what would have gone through your head? Relief that the spacecraft still worked? Awe that it was still sending new science? Or the deeper shock that one old machine had just shown you that the map in your mind was missing an entire layer? Because that is the real power of Voyager 1. It keeps turning assumptions into questions, and the questions keep getting bigger. The interstellar medium matters because it presses against the heliosphere, the giant bubble made by the sun. That bubble helps shape the radiation environment of our entire solar neighborhood. It is not just an abstract edge on a chart. It is part of the reason Earth sits inside a certain kind of cosmic shelter. It does not block everything. It does not make us safe from every high-energy particle, but it matters. Its shape matters. Its strength matters. The conditions outside it matter too, because those conditions push back. So when Voyager 1 tells us that the local interstellar medium is more structured and more active than the old simple picture suggested, it also tells us that the boundary around our solar home may be part of a more dynamic relationship than we once imagined. That does not mean panic. It means humility. It means the space just outside our front door is more alive than we thought. And here's the most unsettling part. And we are learning this from one spacecraft, just one. We do not have a fleet out there. We do not have a network spread across interstellar space. We have one elderly probe listening with fading hardware from more than 15 billion miles away. That is why the next chapter in this story feels almost unreal. Because while Voyager 1 was transforming our picture of interstellar space, it nearly stopped being able to speak at all. In late 2023, something went wrong on board. The spacecraft kept transmitting, but the data coming back no longer made sense. Engineers on Earth were receiving a signal, but not useful information. It was as if Voyager 1 was awake, but talking in broken fragments. The line was open. The message was not. That is the kind of problem that can end a mission, especially this mission. A spacecraft close to Earth can sometimes be serviced, replaced, or at least studied in detail with better options. Voyager 1 is not close. It is so far away that every decision arrives with a brutal delay. Around the time of the repair effort, NASA and JPL said a radio signal took roughly 22.5 hours to reach the spacecraft. and another 22.5 hours to come back. Later, updates put the one-way time at about 23 hours. Think about that for a second. You send a test. You wait almost a day for it to arrive. Then you wait almost another day for the answer. Nearly 2 full days for one round of communication. Now imagine doing surgery under those conditions. That is basically what the team had to do. They traced the problem to the flight data system, the computer responsible for packaging engineering and science data so it could be transmitted to Earth. The culprit was a damaged memory chip, not a movie-style explosion, not some dramatic final warning. Just age, radiation, and the slow cruelty of time catching up with a machine that had already lived far beyond its expected life. The bad news was obvious. Nobody could replace the chip. Nobody was going out there. The good news, if you can call it that, was that the team still had a narrow path forward. They could try to move the affected code into other parts of the spacecraft's memory, but that was not a simple copy and paste. The code had to be broken into sections, stored in different places, adjusted so the sections still worked together, and then linked back into the rest of the system properly. That is delicate work on a computer in the same building as you. On Voyager 1, it was remote brain surgery across billions of miles, and it worked. In April 2024, the team began relocating the code responsible for packaging engineering data. When they heard back, for the first time in 5 months, they could once again check the health and status of the spacecraft. The old machine had found its voice again. I want you to picture that moment in the control room. Not cheering right away, not yet. First, the careful read, the double check, the stunned silence. Then the realization that the spacecraft was answering in a language humans could understand again. After all that distance, after all that delay, after all those decades, that alone would make Voyager 1 legendary. But the story did not end with survival. It returned to science. And the science it is returning to may be the most important kind of science there is. Not because it gives us a simple answer, but because it keeps forcing us to ask a deeper question. What is the true nature of the space between stars right outside our own solar bubble? Even now, researchers do not think the mystery is fully settled. In the 2021 paper, the persistent narrowband emission had more than one possible explanation. One possibility was thermally excited plasma oscillations. Another was something called quasi-thermal noise. Both ideas point to real physics, but they are not identical, and the distinction matters if you want to build a fully correct model of the local interstellar environment. In plain English, scientists know the signal is real. They know it tracks something important, but they are still working out exactly what physical process is producing it. That matters because every interpretation changes the story a little. If one model is right, it tells us one thing about how particles behave out there. If another is right, it tells us something slightly different about temperature, density, and the way plasma interacts with its environment. Either way, the result is the same on a human level. The region beyond the heliopause is not a blank sheet. It is a living system with detail we are only beginning to read. And here is the painful part. The only machine giving us this running real-time window is getting weaker every year. If you love space stories, this is the moment to pay attention, because we may be living through the closing years of one of the greatest scientific listening posts humanity has ever built. Voyager 1 is powered by radioisotope thermoelectric generators. That phrase sounds technical, but the idea is simple. The spacecraft makes electricity from the heat released by decaying plutonium. At launch, the system produced far more power than it does now. But year after year, the power drops. NASA says the Voyagers lose about 4 watts of power every year. 4 watts does not sound like much until you realize how tight the margins have become. By 2026, those margins were so thin that mission engineers had to make another hard call. On April 17th, they shut down Voyager 1's low-energy charged particles experiment, the instrument called LECP. It had been operating almost without interruption since 1977. The reason was simple and brutal. Save power now, or risk losing more later. That decision left Voyager 1 with 2 operating science instruments, one listening to plasma waves and one measuring magnetic fields, 2 remaining scientific voices from a craft nearly 49 years into its mission. And even that may not be the final configuration. NASA says the team is working on a more ambitious energy-saving plan with the unforgettable nickname the Big Bang. The idea is to swap out a group of powered devices at once, turning some things off and replacing them with lower power alternatives so the spacecraft stays warm enough and useful enough to keep doing science longer. The team planned to test this on Voyager 2 first in 2026 because it has a little more power to spare and sits closer to Earth. If it works, a similar approach could be tried on Voyager 1. There is even a chance the LECP instrument could someday be turned back on. Read that again and let it sink in. A spacecraft launched in 1977, now in interstellar space, is still being reconfigured by engineers on Earth who wait almost a full day for their commands to arrive. That is not just engineering. That is endurance as a scientific method. And the clock is still ticking. The one-way radio delay is already about 23 hours. In other words, Voyager 1 is operating right on the edge of a haunting milestone. Very soon, a single message from Earth will take about a full day to reach it. One command, one day out. Another day back for the reply. A conversation stretched across 2 days of silence. No human-made object has ever been farther while still doing active science. And that brings us to the emotional center of this whole story. Voyager 1 is not just a machine gathering data. It is also a message about what kind of species we are. Bolted to the spacecraft is the Golden Record, a gold-plated copper disc carrying sounds and images from Earth. Greetings in 55 languages, natural sounds like thunder and birds, music from different cultures and eras, images of life on this planet, symbols showing where Earth is in the galaxy and how to play the record. People love to talk about it as a message to aliens, and yes, that is part of the romance. But it is also something else. It is a message to the future, a quiet declaration that, for a brief moment in cosmic time, a species arose on a small world, became curious enough to build a machine, and sent that machine beyond its home bubble carrying evidence that it had lived, listened, laughed, and wondered. There is something almost unbearable in that image now, because the record rides on a spacecraft that is both fragile and heroic. Every year it loses power. Every year another choice gets harder. At some point, the last active instrument will go dark. The last coherent signal will leave the spacecraft, spend nearly a day crossing the distance to Earth, and then arrive here as the final line in one of the greatest scientific conversations ever held. After that, Voyager 1 will not explode. It will not crash. It will not announce a dramatic ending. It will simply keep going, silent. Through interstellar space, past regions no human being will ever personally visit, past distances so large they stop feeling like numbers and start feeling like myth. And that is why the science matters so much right now. Because this persistent plasma hum is not just one more weird space story, it may be the first steadily sampled real-time measurement of interstellar plasma density humanity has ever had. Before this, the data came in isolated flashes. Now, thanks to that faint narrowband signal, we have something closer to a running portrait. Not a perfect portrait, not a complete portrait, but a real one. It is telling us that the space between stars has weather, maybe gentle weather, maybe turbulent weather, but weather all the same. It is telling us that our heliosphere is not a sealed bubble floating through nothing. It moves through a medium with structure, variation, and pressure. It is telling us that the old simple story of a quiet void was too simple, not absurd, not worthless, just incomplete. And science advances exactly that way. Not when someone proves everything before was foolish, but when reality turns out to be richer than the model. Voyager 1 keeps doing that to us. It keeps reminding us that the universe is under no obligation to be simple, just because simple stories are easier to tell. So here's the question I want to leave hanging for a moment. If the nearest interstellar environment is already more complex than we thought, what else are we getting wrong simply because we have never been there to listen properly? That question should stay with you, because there is no replacement waiting on the launch pad. Even if a new interstellar mission were approved tomorrow, it would take decades to reach the boundary Voyager 1 crossed in 2012. Decades. That means when Voyager 1 finally falls silent, the real-time window it opened into interstellar space could close for a generation or more. The debate over what exactly produces that hum may remain unfinished. The map may remain partial. The unanswered questions may have to sit in the dark for years, maybe longer, waiting for the next machine brave enough and patient enough to go out there. If this kind of story is why you watch Galaxy Sphere, stay close, because the next big mystery in space will not announce itself politely either. It will arrive as another faint signal, another strange measurement, another quiet fact that forces the whole picture to change. And maybe that is the deepest lesson of Voyager 1. Not that scientists were wrong about everything. They were not. They were right about a great deal, but they were still surprised. And that surprise is the point. The first instrument ever placed in interstellar space has shown us that the darkness outside our solar bubble is not a dead stage between meaningful places. It is a meaningful place that changes the emotional scale of the universe. It means the road between stars is not just distance, it is environment, it is physics. It is a frontier with its own character. A frontier we once imagined as silent and simple, but which is now answering back in a thin, steady hum. Right now, as you listen to this, Voyager 1 is still out there, more than 15 billion miles from Earth, moving at roughly 38,000 miles an hour relative to the Sun, running on dwindling power, listening to plasma waves, measuring magnetic fields, carrying the golden record, sending its delayed whispers home. It is old, it is damaged, it is astonishingly far away. And it is still teaching us. Long after newer machines, flashier machines, and more powerful machines captured headlines, Voyager 1 kept going far enough to reach the place where the old theories could finally be tested from the inside. That may be the most beautiful part of the whole story. This mission did not win by being modern. It won by enduring, one machine a fading power supply, a nearly day-long one-way delay, 2 active science instruments, and still, somehow, new knowledge. So the next time you look up at the night sky, do not picture interstellar space as empty black wallpaper. Picture currents, pressure, charged particles, a strange soft weather moving between the stars. Picture an old spacecraft drifting through it like a tiny metal ear, still listening. And then ask yourself something simple. When the final Voyager signal finally arrives, when the long conversation ends and the silence after it is real, will we have learned enough from the one machine that made it there? Or will we only then realize how extraordinary it was that for one brief stretch of human history, we were listening to the space between stars and it was quietly answering back?